Hello everyone. Today we're going to be looking at properties of triangles. But before we begin that, I'll just go over yesterday's assignment. If you're comfortable with how yesterday's assignment went, then feel free to skip ahead to the start of properties in triangles. Okay, so starting with 1C. Here we are. I give you a little bit of a hint last time. So first thing you needed to do was solve for this missing side length. So you need to use Pythagoras theorem. A squared plus b squared equals c squared. So a squared, right, plus b squared equals c squared. Remember, the hypotenuse always has to be c. Alright, so let's go ahead and substitute what we know. 68.4, 89.5 squared. 68.4 is that. 89.5 squared is that. So a squared, okay. Want to get a on its own, so subtract this thing, right, from both sides. So subtract 4,678 from both sides. So that, then we're just left with a squared on the left equals this. Okay, and then square root both sides. So that gives you a, which is 57.7 centimeter. And there's some more digits in there, but I'm going to leave that unrounded for later. So next we need to solve for p. So we will still have a squared, this is b squared, and c squared will be p. So a squared plus b squared equals, we'll call it p squared. A squared we know, 57.7, and there were some other things in there. B is 46.9, that's the other leg of the right angle triangle. And then we solve for p. So a squared will be the same thing we had earlier. So 3331.69 plus, right, 46.9 squared is this number. That equals p squared. So next add this and this together. So that will give you this number. So that's p squared. Square root both sides, then you have p. So square root of that, 74.4, call it. Everything else seems to be rounded to one decimal place, so might as well let p be rounded to one decimal place as well. Alright, that's 1C. On to question number 2, so the rest of 2 and 3. So solve for the length of side x. So here we have this. The side length opposite that is the opposite side length, and then this is adjacent. So x is adjacent. Looking at your trig ratios, the one that mentions opposite and adjacent is tan. So we're going to go tan 41 equals opposite over adjacent, which is x. We need to get x on its own and upstairs, so if you want, you can multiply both sides by x. So this would be x tan 41 equals 20.2. and then you can divide both sides by tan of 41, so 20.2 divided by tan 41. So 20.2 divided by regular tan of 41, okay, not tan inverse. So we get 23.2 millimeter for x. All right. By the way, if you were doing tan 41 separate, you should get something like 0.869 and so on. So 20.2 divided by that number gives you that thing. Okay. Next, solve for x here. This is our reference angle. That would be opposite. This is adjacent. And x is hypotenuse. That's the one opposite the right angle. Okay, we don't have the opposite length in this case. Doesn't matter, we don't need it. So adjacent and hypotenuse. So which of the trig ratios uses adjacent and hypotenuse? It's going to be cosine. So we got to go cosine of the angle 62 equals adjacent 3.3 over hypotenuse. So I guess we can call it x. So 3.3 over x. Same basic procedure as the question we just did, right? You bring x upstairs by multiplying both sides by x. So we would have x equals 3.3 divided by cos 62. So I just did it all in one step, right? It's the exact same thing, basically, except instead of tan, we have cos and some other numbers, but the general procedure is about the same. So next we're going to go 3.3 divided by cos of 62. So you should get 7.029, so maybe just call it an even 7.0, and we're done. So by the way, cos of 62, something like 0.46947, so on. Okay, but we needed x, so there we go. Okay, on to 3. So solve for the measure of angle A. Angle A is there. Opposite is that, and then adjacent is that. We don't have the hypotenuse, we don't need it. Which of the trig ratios do we need? So we have opposite and adjacent, and we want this angle theta, or A as it's called here. So which one mentions opposite and adjacent? It's going to be tan again. So tan of the angle A is opposite. So 5.1 divided by 8.3. So tan of A equals, alright, so let's figure out what that is. 5.1 divided by 8.3 is 0.614 and so on. And if we want to solve for A in this equation, we need to take tan inverse of the number on the right, 0.614, so on. So I still have this in my calculator. I do like a second tan or shift tan, and then of the answer. So tan inverse of what I just got is 31.568. Call it a 31.6 meters. Nope, it's not meters. Just about made a mistake there. Okay, so we're solving for the angle, right? So it should be degrees. It's a little bit different to the questions that we just did where we were all doing lengths. So it's getting a little bit procedural there and forgot what I was doing. Okay, this one, again, we need to solve this angle. We have, so the angle opposite the right angle is the hypotenuse, and the angle opposite the reference angle is the opposite. So which of the trig ratios mentions opposite and hypotenuse? So toa, opposite, hypotenuse, sine. So sine of A equals opposite over hypotenuse, so 17.3 over 25.8. So you can figure out what that is. Just do 17.3 divide 25.8. So that's 0.6705, some other digits. We need to take the sine inverse of this number to figure out what A is. Sine inverse of that thing. So 42.1 degrees. And I just rounded to the 10th because everything else is to the 10th, so why not? Okay, last one there, 3C. Need to solve for this one. The side opposite the right angle is the hypotenuse. The side adjacent to the reference angle that's not the hypotenuse is called the adjacent. So which of the trig ratios would you use in this case? You need cosine. So cos A equals adjacent, which is 80.4, divided by hypotenuse, 129.5. Alright, figure out what the right side is. 80.4 divided by 129.5. You get 0.62. 0849, so on. Okay, we need to take cos inverse of this number in order to figure out what A is. So cos inverse of 0.6208, so on. So second cos 51.6. Alright, so that's the assignment done from yesterday. And we're starting on properties of triangles today. Property is a characteristic that classifies the object and distinguishes it among other objects of its type. What properties describe a triangle? So it has three sides. It's closed, so closed meaning this would be an open, right? There's like a gap where it's not connected. Same thing with that. Like these are both three-sided shapes, but they're open. So that's a distinguishing feature of triangles. The other thing, the sum of the interior angles is 180 degrees. So that's always true, no matter what. So it could be a right angle, isosceles, and so on. Okay. Right, so looking at a few specific types of triangles. So by angle measure, an acute triangle is one where all three angles are less than 90. So each one of these is less than 90. Next type of triangle is a right angle triangle. So one of the angles is 90 degrees. And this, by the way, is where Pythagoras' theorem applies. This is also where sine, what am I doing? Sine, cosine, and tangent work. So katoa. These only work in right angle triangles, right? There's ways that you can sort of make a 90-degree triangle out of others, but these directly apply to right angle triangles only. Okay, and obtuse, you have one angle greater than 90, so these are both less than 90. This one is greater than 90, so that is 90, and so on. Okay, so those are classified by angle measure. Okay, next, classified by side length. There are equilateral triangles, so those are ones where we have three sides that are equal length and three angles of our equal measure. So each one of these lengths is the same, and each one of these angles is the same. So given that all the angles add to 180, if you split that evenly among three angles, that's got to be, they each are 60 degrees in a equilateral triangle. Okay, isosceles, you have two sides that are of equal length and two angles that are of equal measure. So you got two sides that are the same, this one's something different, and then you've got two angles that are equal. So by the way, if you ever want to this is a helpful fact. So if you have only given to you that these two side lengths are the same, you know right away that these angles are the same. Okay? And similarly, if you only know that these two angles are the same, you know right away, if it's a triangle, that these two side lengths are the same. Okay? And then the last, based on side length, is a scalene. So this has all sides are of different length and no angles are of equal measure. So looking at all these angles, they're different. Looking at all these sides, they are also different. So so those angles are different. Okay, so that'll be useful for us. Triangles are useful in construction and manufacturing because of their strength and rigidity. So we'll look at triangles in use in the real world. Okay, so looking at example 3, use the following diagram to answer the questions below. What is the length of side BC? So BC goes from here to here. Alright, so with this triangle we can use our knowledge of isosceles triangles. We know that this side length is equal to that side length, so therefore, so this one is 20, C is also 20, and because these two lengths are the same, that means this angle is equal to that angle, so that means that is 53 degrees. Okay, so triangle ABD is what we say as is congruent to triangle ADC. So they both have a right angle. They have a common height. So that, and so basically what we could do is say, all right, so because this is 53, this is 90, this one's going to make up the rest of it. So that angle up top is going to be 37 degrees. And it's going to be the same for this one here, so 37 degrees. So we could say triangle ADB is congruent to triangle ADC. Because of, and I guess we can just take our pick. So one of the ways that we know that a triangle is congruent to another one is what's called side angle side. So if you have a side, an angle, and a side that are the same for two triangles, so side, angle, side, so they have to be adjacent to each other, right? They have to be side, the angle in the middle, and another side. So that means those two triangles are congruent. So anyway, that was kind of a little bit more possibly than what we needed. But it's going to be important because basically, if we know these two triangles are congruent, that means I know that BD is equal to DC. So basically, if I look at this triangle here, and I solve for x, I can basically just multiply that by 2 because I know that this is also x. Okay, so let's go ahead and figure out what x is first. So we have a reference angle here, which is 53. We have the opposite, so opposite there is 16, and we have the hypotenuse. So which of the trig ratios do we need? Opposite and hypotenuse, we're going to use sine. So sine of 53 equals opposite 16 over 20. Hang on, that's not the right approach. Let me rephrase that. Okay, we need x. I was just about to make an equation that was just gonna give us nothing. So anyways, maybe need more caffeine. We need the adjacent side length. Okay, we have the opposite side length, we have the hypotenuse side length, and we have a reference angle. So we need something that includes the adjacent. So sine is going to give us something useless, as I just showed. There's no variable to solve for. So we could either use cosine or tangent to figure out what x is. So why don't we go with tan? So tan 53 equals opposite 16 over adjacent x. Okay, and then multiply both sides by x, and then divide both sides by tan. So they basically swap places. So tan 53. So 16 divided by tan 53, 12.06. Could maybe call it 12.1, so centimeter. All right, and then BC is equal to 12.1 times 2, so it's going to be 24.2 centimeter. All right, and classify triangle ABC by angle measure and by side length. So let's look. So triangle ABC is this big one. So it's that. We have two sides are the same. They're 20. If it turned out that this other side was also 20, we would have an equilateral triangle. But that's not the case. So by angle measure, what is it going to be? So let's have a look at our handy dandy reference here. So there's no angle that's greater than 90. There's no angle that's equal to 90, and all of them are less than 90, so it's acute, right? So this was 53, this was 53. These ones both turned out to be 37, which if you add them together make 74, which is less. So triangle ABC is acute. So that's based on angle measure. And triangle ABC is isosceles because two of the side lengths are the same. So isosceles. So question number 4, use the following diagram to answer the questions. what's the measure of angle M? So let's have a look here. This is an isosceles for sure, triangle, so 15, that means this side is 15, that's what those ticks mean. Now because this is an isosceles triangle, we know that these two side lengths are the same. That means that these angles are the same as well. So if this is 60, that's 60. Okay, and then knowing that the sum of all the angles in a triangle add to 180, what we can do is subtract these two from 180 to figure out what angle M should be. So basically 180 minus 120, that's 60. So it turns out that this triangle is an equilateral because all angles are the same. So it is an equilateral and acute. So based on angle measure, it's acute. Based on side length, it's equilateral because all the sides are the same. Okay, number 5 and 6 you should do for your assignment today. So number 5 and 6. You can have a read through example number 4 if you like. It's worked on the next page here. And we'll go through example number 7 at the bottom of page 185. Okay, so there's a truss bridge. Diagrams here, so you can see these double tick marks mean that all of these lengths are the same, right? There are 1, 2, 3, 4, 5, 6 of them. First off, how long is the bridge? So if we focus in on just one of these triangles, so if you look at this one, it's a right angle here. If we can figure out just this length here, we can take it and multiply by 6 to get the full length of the bridge. Alright, so we have this length, which is the hypotenuse, and we have the height, which is also here, so this is 8 feet. So we have one of the legs of this right angle triangle, and we have the hypotenuse, so we can use Pythagoras theorem to figure out what the missing side length should be. So remember that C should always be the hypotenuse, so you should sub in 11.3 there. And then the other two, the order doesn't matter, so you could sub 8 in for B if you like, or you could sub it in for A. I'm going to do it for B. And let's solve for A now. So 8 squared is 64. 11.3 squared is 127.69. So that's A squared. And we want A on its own, so we can subtract 64 from both sides. So subtract 64. That gets rid of it from the left, and then we have now just A squared on the left, and 127.69 minus 64 gives 63.69, and then we square root both sides to get A on its own. So the square root of 63.69 is 7.98 feet. Okay, are we done? Not quite. We have now this length, 7.98 feet, and we need to multiply it by 6. So multiply by 6, and we get 47.88360889. So maybe I'm just going to round it to the nearest tenth. So 47.9 feet is the length of the bridge. 47.9 feet. Okay. Calculate the interior angles of triangle ABC. So ABC is, maybe do it in a different color. ABC is this one. Try to draw it a little better. Nah, not much better, but I tried. So notice we've got two right angle triangles. This and this we could also call, so we can split it up into two right angle triangles, right? Or noticing that these two side lengths are the same, that means angle B is equal to angle C. Alright, and from over here, looking, the single tick represents 11.3, so these are both 11.3. And then the height is the same here, so that's 8. And with that information, we can figure out quite a bit. So basically, if we take this and rotate it, so let me try to do that. If we take these things and rotate it, that's what I'm going to do down here, right? So that's my strategy for this question. So again, this is 8, this is 11.3, that's 11.3. These angles are the same, that's a right angle. So calculate the interior angles of triangle ABC. So we can maybe just focus in on this triangle. We have, so we need the angle in here, so maybe what would that correspond to? So if I rotated this, that would be B. So that would be B, and that would be C, and that would be A. So I just flipped it. Okay, so we have now the length opposite angle B, which we'll call opposite. We have the hypotenuse, which is always opposite the right angle. So which of the trig ratios should we use to figure out angle B? We have opposite and hypotenuse. That's going to be sine. So sine of B is equal to opposite 8 over hypotenuse 11.3. 8 divided by 11.3 is 0.707, and then some other digits after that. Sine B. And if we want to figure out what B is, we need to take the inverse sine of 0.707. So inverse sine of that is going to be 45.1-ish degrees to the nearest tenth. It gave me 45.069, so that would round to 45.1. Okay, and we can say that angle B equals angle C, which is 45.1 degrees, because this length is equal to that length, which means the angles opposite them need to be the same. That's the only way we could have such a situation happening. So C is 45.1 as well. Okay, and then given that this is a triangle, all of these angles need to add to 180. So we can go 180, subtract 45.1, subtract another 45.1, and that's going to give us then, let's see, 180 minus 2 times what I had earlier, 89.86, so 89.9 degrees. Alright, And okay, so based on that, it's just acute. So this is pretty close to a 90. So this one is almost 90. It's a little bit less though, so it's just acute. So based on the angle, triangle ABC is acute. All angles are less than 90. Just less than 90. And by the way, these angles that I just subtracted, I used the unrounded version of my answer from here, so I just multiplied that by 2 and subtracted that from 180, so that's how I got that. Okay, so that's good. ABC is acute, and next thing we should check is based on the lengths. So we can check maybe to see what this length is, just for curiosity. So you can do Pythagoras theorem on this. So 11.3 squared minus 8 squared, which is 64, square root that. So it turns out that this is 7.98. So then that full length down here is 15.96. So 15.96 isn't the same as 11.3, so we can rule out the fact that it's a equilateral based on that. But we could also rule out the fact that it's an equilateral because the angles here aren't all 60. So the other thing we can say about triangle ABC is that it is isosceles. Right, two angles are the same. So angle B equals angle C. Okay. Oh, and that's what we had to do here. Classify ABC and ABD. So I already did for ABC. And then ABD is a right angle triangle, so I'll just do the rest on the same page. So triangle ABD is, it's got a right angle here, so it's right. And we've got 8, 11.3, 7.98. So it's very nearly another isosceles triangle, so it's almost, but not quite, where this side is equal to that side. So depending on how much you're rounding to, you could go ahead and say that triangle ABD is isosceles, right? But it's not quite there. So I don't know. If you want to round this to an 8, you could say it's isosceles. But there's no direction from the question saying round to the nearest tenth or whole number or whatever. So we got a little bit of freedom here. So because it's not perfectly 8, I'm going to say that it is scalene. So scalene again means that all sides are of a different length. Okay, so you can use this and the one on the previous page quite a bit for today. You'll make use of this. Keep using your Pythagoras theorem and the trig ratios, and that'll be it. So if you could do these for this evening or today, take a picture of your work, submit it, and I'll see you next time.